Well, good morning. My name is Yancy Young. I'm with the ISS Payloads Office at Marshall. Unlike the previous presenter, I am not a structural biologist or a crystallographer. I am an engineer, so I want to try to get through this the best I can to talk to you about the influences of microgravity on the growth of macromolecules, as well as the benefits we have seen in the post-flight data. And if I cannot answer any of your questions, feel free, my email's here, or you can get with me after this session, and I can do my best to get you in touch with the right people to talk with. Next chart, please. Okay, biological macromolecular crystal growth, which is a mouthful. And in more generic terms, we refer to that as protein crystal growth, which it actually encompasses more than proteins. It's proteins, nucleic acids, and viruses. And basically, there's tens of thousands of these macromolecules in every living thing. And they all perform a function. Some are beneficial to life, make life possible. Some are detrimental to life. And basically, the goal of PCG, and I'll use that throughout the presentation generically, is to determine this three-dimensional structure of these proteins, and by determining the structure, determining the function of that protein, and either ways to enhance it or to inhibit it. Now, there have been advances in diffraction sources, protein preparation, that have allowed more to be done with smaller crystals, but there still seems to be even the smaller crystal, getting one of the right size and the right order still is the major roadblock for most protein crystallographers. Next chart, please. So what is the difference between a laboratory environment and a microgravity environment when it comes to the growth of protein crystals? One is, like Dr. Pellis had touched on earlier, is the reduction of buoyancy-driven convection and sedimentation. As you can see in the figure here at the top right of the chart, this is a lysozyme crystal grown in 1G environment. And what you see is as the nucleus of the crystal forms and the molecules, the protein molecules are added to that nucleus and the crystal begins to grow, there's a slight halo around the crystal. This is the region of where the protein or the density of the molecule is depleted as those molecules are added to the crystal, and the more molecules are added to the crystal, the lighter that region becomes, and with buoyancy-driven convection, that will rise up, as you can see the growth plume in photograph D here. And what that in turn does is now, instead of that crystal surface being exposed to a region of low concentration, which a diffusion limited growth rate, is now subjected to the higher supersaturated concentrations, which will, one, rapid growth, two, will enable misoriented molecules to be trapped into the crystal lattice, thus you have a lower quality structure. Also, a second theory or effect of microgravity on protein crystal growth is the reduction in secondary nucleation, which is also believed to be caused by the effect of the convective flows in a 1G environment, where you may have a cluster of molecules right at the surface of the crystal. The convective flows is taken away somewhere else into the solution, where it forms a nucleus and it begins to crystallize. So now you have multiple crystals in one growth chamber, all competing for that precious resource or the macromolecule of interest. And the third is sedimentation. What's been seen on the ground, usually between the size of 10 to 100 microns, once the crystal starts forming, they will settle out to the bottom of the growth chamber. And what that basically results in is you have restrictions into what size of the crystal additional molecules can attach, so you wind up with a distorted crystal structure. Next chart, please. So these were, what I'm getting into now is some results that from previous microgravity research And these were the improvements that they saw in the diffraction analysis of the crystals post-flight. And there were three things: increased resolution, decreased mosaicity, increased volume. And I'm going to start from the bottom and go to the top. Of course, increased volume means you have more of the protein molecule in the crystal structure. More protein molecule means more atoms, means more X-ray diffraction. But that's only half the story, because you can have a large crystal, it can be a very low order, and you wind up with, let's go to the mosaicity, or the angle of difference between the individual molecules, which will affect your X-ray diffraction data by, you have what's called spot repeats, because as you rotate the crystal in the X-ray diffractor, that one atom may stay in that beam longer than the one that's in others, so that same spot gets repeated over and over again, so it skews your data. And then, of course, increased resolution, which I think is a product of the first two, is just the level of detail that you get in your X-ray diffraction pattern, and then eventually your X-ray diffraction pattern, which more detail, you can pick out the actual atoms within the atomic structure of the protein itself. Less detail, you can pick out the contours of the protein. Next chart, please. Here's an example of some research that was done on STS-95. This is a 9-day mission. The target macromolecule is insulin. As you can see from the photographs, the top being the microgravity, of course, bottom being ground, these are both under the same magnification. First of all, you've got a larger crystal volume with the microgravity grown compared to the ground. Then, as you can see on the top scatter chart, it shows the mosaicity angle. You can see that the dark dots, the microgravity produced crystal, much lower mosaicity in the crystal. And then, as a result, like I said, of the previous chart, the increased volume, the more ordered the structure, the more intense the diffraction pattern. Next chart, please. Here's a few examples of some actual crystals that were grown. The top was antithrombin 2, which performs a coagulation function. It's the target of thrombolytic disease and stroke. And this was, once again, this is a 9-day mission, and it refracted to 1.8 angstroms, which at that time was the highest for that particular protein. And the bottom one is a insulin drug complex that was grown. This is a shuttle mission as well. I'm not sure the duration, but the principal investigator, Dr. DeLucas at UAB, the microgravity on crystals on the right, which are much larger, produced a more accurate mapping of the structure. And then the last part there at the bottom, Dr. Kundrat and others did a study. They went out and looked at all the reported findings from shuttle missions of protein crystal growth to see what percentage improvement they see post-flight in diffraction data. And what we call the repeat flyers, the frequent flyers, as you can see, the more times they flew, the higher percentage of improvement in the diffraction data was achieved. Unfortunately, there were some proteins may have only flown once for some reason. And the principal investigator might have been discouraged and didn't come back. So the more you fly, the more you can learn. Next chart, please. I won't go through all these. I may should have struck the word new off the top, the front of this chart, because these were all shuttle-based success stories for protein crystal growth and microgravity. Next chart, please. But you will see at the bottom of the chart, there's the references where you can find those. Thank you. Okay, here's a few examples of some protein crystal growth hardware that is a candidate possibly to be reinstated, so to speak. The first one is the protein crystallization apparatus for microgravity. This is a sitting drop vapor diffusion method for protein crystal growth. These have flown several times on shuttle, I think on Mir and possibly on space station. But basically you have 63 individual experiments per cylinder. And these have been flown both in ambient and under thermal control. The sample well ranges in size from 5 microliters to 40 microliters, and that's surrounded by a wicking material that contains about 500 microliters of your precipitant solution. Once those are loaded on the ground, there's an elastomer membrane that actually deactivates the experiment. And once you get on orbit, you can see here in the picture of the hand, it's just like a ratchet wrench. You turn that and it activates all 63 experiments at one time by removing the membrane. And that is, the hardware provider for this particular piece of hardware is Dr. Daniel Carter of New Century Pharmaceuticals and also the Marshall Space Flight Center. Next chart, please. The second one is the Enhanced Diffusion Control Crystallization Apparatus for Microgravity. That's another mouthful. But this one is either can be dialysis or liquid-liquid diffusion. This is actually an enhancement to the diffusion-controlled crystallization apparatus for microgravity. It flew several times on the air very successfully. This particular piece of hardware has not flown before, but it is more ideally suited to grow the larger protein crystals or macromolecular crystals that are ideal for the neutron diffraction, which is slightly different from X-ray diffraction. In neutron diffraction, you can actually detect the hydrogen atoms in the structure. This is also Dr. Daniel Carter from New Century Pharmaceuticals. Next chart, please. Oh, and by the way, the PCAM and EggCam hardware, I believe, are over in like the Teledyne Brown exhibit, so if you're interested, you can go over and look and they can provide you more detail. The high-density protein crystal growth, this is hardware provider is Dr. Larry DeLucas, University of Alabama, Birmingham. I believe there will be a presentation tomorrow on the specifics of this, but basically there's 1,008 vapor diffusion cells housed within a Merlin. The protein volume can vary from 5 microliters up to 40 microliters, the precipitant of half a milliliter up to a milliliter. And they can activate roughly 226 of these experiments at one time, so that means you could stagger the activation or deactivation depending on your profile, your growth profiles. Next chart, please. The last is the observable protein crystal growth apparatus, and this one's a little bit different than the previous. This is a liquid-liquid diffusion experiment, but in addition to growing the crystals of interest, it also incorporates interferometry and polarizing microscopes to try to capture and record the formation of the depletion zone that surrounds the crystal, which is one of the hypotheses of why the crystals grow more perfect in space. There's 96 cells total for this apparatus, is liquid-liquid diffusion. And I think that's all. And Mr. Greg Jenkins over here, who is the engineering or panel developer for this particular apparatus. So if you want to talk to Mr. Jenkins, he can provide you with more details on that. And then the next chart. I think this is my last one, so I'm really getting you guys ahead of time. Basically, the examples I've shown previous in the presentation are more or less all station results, or not station, I'm sorry, shuttle results, shorter mission durations, I'd say no longer than 16 days on average. Now that we have station fully or almost fully assembled, 6-man crew, this is, I think an ideal situation for extended crystal growth durations for our target molecules. And then last but not least, put a quote in here, I hope Mr. Hopman doesn't mind, but he too, I think this is back around STS, I want to say 95 or 97, but as you can see from his quote in his letter to the U.S. House of Representatives, Mr. David Minge, that he too was, like many people are in this area, we're very skeptical about the advantages that microgravity could offer in protein crystal growth. I think after his experiences with flying on a shuttle, that he could see that this is definitely, opens up an alternative to obtaining crystals that you might not otherwise be able to obtain on the ground. And that's all I got. Well, that went right over my head. I don't know if
Yes, it would be a macromolecular assembly. Like, for example, the study of the structure and the analysis of the structure of an enzyme with its substrate attached to it. This has been done before, but I'm just wondering whether this has been done.
Oh, well, I mean, they do fly, like I said, as complexes of molecules, yes. But now the specific results I could not comment to. Any more questions? Okay, thank you.